Welcome to lecture 24 for a first year chemistry class, either a high school or an introductory class at the college level. This lecture is on nuclear chemistry, and for the class that I'm currently teaching and using this video for, what I'm doing here is actually taking this topic to a little bit of a higher level using the same notes that I would use in a general chemistry class. Most of the time, nuclear chemistry gets very short shrift in a chemistry class. It's usually done at the end, just like we're doing. And if you run out of time, most teachers or professors just decide, well, it's really not something that most chemists do, and most students really don't need to know a whole lot about nuclear chemistry. It's also a physics topic. Actually, most of the nuclear, it's definitely a area where chemistry and physics mix. A lot of nuclear chemistry is done in physics departments. So we're going to spend a little bit of time. It is an important topic. It's in the news a lot. Nuclear reactors, nuclear bombs, the harmful effects of radioactivity, those kinds of things can only be understood if you've at least had a little bit of background on nuclear chemistry. So what we're going to do is we're going to start off with the familiar symbol here from your first time of seeing nuclear chemistry. And generally that's when you talk about the nucleus at the beginning of a discussion of the atom, and you talk about mass number and isotopes and atomic number and what those things mean, and you write these symbols. And that's pretty much where it's left. And so now we're going to pick up and talk a little bit more about it. The topic that I talk about right here in this introductory paragraph is the most important nuclear reaction to life on Earth, and that is the nuclear reaction of fusion that goes on in stars, which gives us our light that we must have for life. Our sun fuses hydrogen nuclei together in a nuclear fusion reaction, and the fusing of those two light nuclei produce a tremendous amount of energy. The most abundant element in the universe is hydrogen, and once all the hydrogen has been used up in a star, then it starts fusing helium together to form nuclei that are heavier and heavier, up to about, I think it's nickel. And then from that point on, you don't get any heavier elements unless a star goes supernova, and then you get some heavier elements. So, birthplace of the elements found on planets begins in the stars. All right, so nuclear symbol, should be familiar. Mass number on top, number of protons and neutrons, atomic number on the bottom, number of protons or electrons if your atom is neutral, and we'd write those numbers on the left. Now, what we're going to experience here in nuclear chemistry is that for this topic, there is some new terms. We've used the term isotope before in earlier discussions on the nucleus. Nuclear chemists call any particle in the nucleus, that being protons and neutrons, they call them nucleons. And remember that the mass numbers are not on the periodic table. An isotope, instead of using the word isotope, I'll probably use it interchangeably. They use the word nuclide, and a nucleus that is radioactive is a radionuclide. What I've got here in this table is just a little table of terms and symbols that are going to be important in our discussion of nuclear chemistry. The symbols part is, it's different. Protons and neutrons, those nucleons that are in the nucleus. A proton is usually given in nuclear equations, which we're going to explore in a little bit, are given the nuclear symbol for hydrogen with a mass number of 1. And the reason for that is because that isotope of hydrogen with a mass number of 1, well, it has 1 proton, so that means it has no neutrons. And if that atom of hydrogen has lost its electron, then we call that atom a proton. And you saw that in our discussion of acids and bases. Hydrogens being transferred between acids and bases are referred to as protons. Acid, being the hydrogen ion, is essentially a proton. And then the neutron excuse me, is given the symbol 1 because it contributes 1 to the mass number, and 0 because it does not contribute to the atomic number. So that's why the symbol for a neutron is 1 on top, 0 on the bottom. Alpha particles, beta particles, positrons, and gamma radiation are all radioactive particles. An alpha particle is essentially a helium nucleus, so that is why it's given the symbol of helium with a mass number of 4 and atomic number of 2, which means that an alpha particle has a 2+ charge. Probably something I should put off to the side, so I'll do that now while we're talking. +2 charge, pretty massive particle. An electron or a beta particle has a 0 on top because it does not contribute to the mass number, which is only protons and neutrons, and -1 on the bottom because of what happens in the nucleus during beta radiation. Okay, and that has a charge of -1. A positron is the opposite of an electron. So again, 0 for a mass number, but +1 for a charge. Oops. And a gamma particle, it's not really a particle, it's a photon, it's radiation, has no particle numbers, no mass. Okay, so let me put that off to the side. All right, so important additions to our table. So as we have discussed a little bit about terminology, it's time to start thinking about talking about radioactivity, and then at the end of our discussion here, we'll return to fission and fusion just very briefly. We could spend a lot more time on nuclear chemistry, but at least we're spending a little bit of time. Most nuclei and atoms are stable indefinitely, but radionuclides are unstable and emit particles in order to become stable. Radioactivity is the term for the particles and the energy that are released by these unstable nuclei as they are trying to become stable. So what makes a nucleus unstable? Well, think about what a nucleus is. It is a small, very small area where you have shoved protons and neutrons in, very, very small space. Protons don't like each other. So therefore, it takes a very strong force in order to hold those together. And the neutrons, it turns out, are intimately involved in generating this attractive force. As you get a larger number of protons, you need even a greater number of neutrons in order to counteract the repulsive forces between the protons. So we see that with atoms up to 20, about an even number of each gives us a stable nuclei. Past atomic number 20, the neutron to proton ratio increases rapidly, and this can be seen from this figure that I'm about to show you. Anything with a nuclei with an atomic number of 84 or higher are radioactive. And a little bit of information for you. If you look at your periodic table, no elements after uranium with an atomic number of 92 had been discovered prior to World War II. And the reason for this is during the development of the atomic bomb, a lot of research was done on radioactive particles and so on, and so more elements were discovered. And what we're looking at here is what's called the band of stability. It's the number of neutrons versus the number of protons. So when you have an equal number out here, as we said in the paragraph above, up to about atomic number of 20, it takes, your slope, you're at about a 45-degree angle here because it takes equal numbers of protons and neutrons. Now, if you draw that red line, you can see that as we get higher and higher numbers of protons, we depart from that equal number thing very quickly, so that we're getting a steeper slope because of the greater need for neutrons. And one important thing to note about this graph is the blue dots represent stable nuclei, Nuclei above the belt of stability. So anything that falls, here in the yellow, that's not a blue dot, beta emission is your primary form of decay that those atoms use to become stable. If you're below the belt, the this blue line, the line of blue dots, then positron emission or electron capture is your primary mode of decay. And then up here with atomic numbers greater than 84, you get your dominant mode of decay is alpha emission. So this just gives us an idea of why certain atoms are unstable. It is because of the numbers of protons and neutrons, and depending on what those numbers are and where they fall on this graph will tell us what type of decay they're going to have. All right, so we're gonna write nuclear equations, and we're going to use those symbols that we had earlier at the very beginning of the lecture. So we're going to have those mass numbers and those atomic numbers. A couple of new words for us. The thing that I've just highlighted would be called the parent nuclide, the parent isotope, the radioactive isotope. And the one on the other side is called the daughter, or daughter. There may be more than one if you're splitting it into two. The daughter nuclide is on the product side. This equation here shows a neutron being absorbed by the silver atom. What has to happen in these nuclear equations, and this is rather easy, is that as with everything else in chemistry, mass is conserved. So mass number, as you go across the table, has to add up to 100. As you go across this equation, has to add up to 105. 105 plus 1, on the reactant side, the parent side. So we have to have 106 on the product side. So the daughter nucleus has to have 106 as a mass number. And then our bottom numbers are conserved as well, the atomic numbers, and 47 and 0 add up to 47. So nothing changed here in terms of the element. So one thing that I always think about when I'm writing nuclear equations and so on is that nuclear chemistry and radioactivity in particular is kind of the culmination, if you will, of the desire to change one element into another, which the alchemists did for a couple thousand years. We're after trying to change lead into gold and so on. Nature's doing it naturally through radioactivity. Radioactivity is a natural process where unstable nuclei strive to become stable. And they do. And we'll talk a little bit more about that in a moment. Okay, one more thing before we do some nuclear equations, and that is just a little bit more terminology. At this point in chemistry, we use quite a large number of words to show that something is a product. Giving off, produces, releases, generates, emission, loss of electrons in oxidation is a product. Add the word decay. So when we talk about radioactive decay, we are talking about products that are formed. All right. Words that imply reactant include absorbs, combines with, not as many for reactants, but add capture to this list. So there is a type of radioactive decay called electron capture, and the electron would be a reactant. All right, so let's look at some nuclear equations. Remember that an alpha particle, that's one we're going to start with, is essentially a helium nucleus. So if something undergoes alpha decay, the alpha particle has to be a product because the word decay means product. Well, if you have an alpha particle as a product, you have a daughter nucleus that has to add up to with the alpha particle to the parent nuclei. So in this equation here, 238 is the mass number on the left side. The two numbers on top on the other side have to add up to 238. The same thing is true for the atomic number. 92 on the bottom on the left. On the right, you have to add up to 92. Beta decay is the loss of an electron or a beta particle. And so all of the same things we just talked about in terms of conservation of mass number and atomic number apply. A positron emission implies that the positron is being emitted, which is a product word, and so it is on the right-hand side of the equation. Gamma emission is the loss of a gamma ray or gamma photon, which is high energy radiation. Almost always accompanies the loss of a nuclear particle. We often do not put it into the equation since it has no mass number or atomic number. If I am doing electron capture, then my electron is a reactant. And so I would write a nuclear equation like this one. If a proton were capturing an electron to become a neutron, this is exactly what happens in electron capture. A proton in the nucleus captures an electron to change into a neutron. So nothing happens to the mass number because all you've done is change a proton into a neutron. The same types of things happen in nuclei when you do either beta or positron emission. Instead of a proton changing into a neutron is changing into a proton. No, yes, all right, because so your mass number doesn't change, but your atomic number goes up, and that's true for beta decay. So you had 53 protons before, now you have 54. That means that we gained a proton, and that was because a neutron changed into a proton, and in the process emitted a beta particle as well, but your mass number did not change because this is protons and neutrons. Positron emission, you're doing the same. Let's see, you're going from 6 protons to 5, so you're losing a proton. So a proton must be changing into a neutron. Mass number doesn't change, and a positron is emitted as a result of that. Okay, large radioactive nuclei greater than 84 often, I'm going to make this larger, often undergo what's called a radioactive series, and where you take a radioactive element like a nuclide of uranium and you do a series of changes in order to arrive at your stable nucleus of lead. Lead is often the end product of a radioactive series. So what it's saying here is each blue arrow is alpha. Remember, atomic numbers greater than 84 primarily use alpha emission if they are unstable. So because that gets rid of a lot of extra protons and neutrons especially. So at the beginning of the radioactive decay series, there is a lot of alpha emission, and the red arrows are beta emissions. We'll do a few problems where we do that, a series of reactions. The kinetics of radioactive decay is pretty straightforward. Now, in the course that you are finishing up, we did not really talk about kinetics, but in order to really look at half-lives and so on, which we're going to talk about in a moment, you really have to think about the kinetics of what's going on here. We could do some really simple problems, and we'll talk about that when we do the problems, but radioactive decay is a typical first-order decay process. And we need some equations to help us be a little bit more sophisticated about determining how much of something is left after a half-life has passed. So what is a half-life? Half-life is the amount of time it takes for half of a radioactive substance to decay. So after one half-life, you'd have half of what you had. After 2 half-lives, you'll have a quarter of what you had, and so on. All right. Carbon-14 dating, which I know you've heard about, is a way of using half-lives, a known half-life, to estimate the age of things. So what happens in radioactive dating, and the way that it works is this: an organism or a rock or whatever, some substance, it is either made up of carbon-14 from the beginning of its existence, and then that carbon-14 decays over time with a half-life of 5,015 years, so that after 5,715 years, there would be 1/2 of the carbon-14 that was originally there. After twice that, there would be a quarter. After 3 times that, and so on. So the way that it works with organisms is they are, as they live, they take up carbon from the atmosphere, either not from the atmosphere, plants do. Animals would take it from the plants that they eat or the animals that they eat. And at the time of when they existed, at the time when they lived, there was a certain amount of carbon 14 that existed in the upper atmosphere that enters the food chain, enters the organisms or plants that they're eating. Okay. And we have, so then that's a constant. It's a constant uptake. When they die, then that uptake is no longer happening. And so then it decays. And when we look at how much is left, we can compare that to the atmospheric amount, and we know how much time has elapsed. So that's kind of how that works. And carbon 14 undergoes beta emission to produce nitrogen. And that is not 314, that is just 14. I made another similar mistake elsewhere in the problems. All right, so it's a first order process. So if you drew a graph, it'd be a nice exponential drop in the amount. The rate is proportional to some constant times the amount that you had. Rates in nuclear chemistry are called activities, and they're measured in becquerels after Henry Becquerel, who discovered radioactivity. So that's what a rate would be measured in. N is the amount, and it can be either in milligrams or atoms or whatever. The integrated rate form for a first order process is this. The natural log of whatever it is you're talking about, the nucleus, the nuclide at time t over the initial, that's what the 0 means, is equal to minus this constant k, a rate constant, times the time that has elapsed. So you can get the k that you need by knowing the half-life and plugging into here and then taking the k and plugging into this equation, and we're going to do a few of these when we do our practice. All right? Energy changes in nuclear reactions. I know that you have wondered about this equation and wondered, when am I going to learn about it? Well, if you really want to learn about it, here's a great book. I have read it cover to cover. It's actually very interesting about the equation. Everything about the equation, even the equal sign. But what Einstein's famous equation is about is the proportionality between energy and mass. And is proportional through the speed of light. Crazy, I know. How did he come up with that? So in typical chemical reactions, we've always said law of conservation of mass. It doesn't change. It can change a little by a very small amount, 9.9 times 10 to the minus 9. You will get some energy out of that. But if you're talking about nuclear changes, nuclear reactions, we get a bigger mass change and we get a huge amount of energy. So, calculating it. The mass lost in nuclear reactions is larger. So for a typical alpha emission, the mass lost, product minus reactant, is this much. That is a lot larger than 10 to the minus 9. That's 4.6 times 10 to the minus 3. You plug that into the equation. You got to cook the mass in kilograms, so the energy comes out in joules, and you end up with negative means you've given it off, exothermic, 10 to the 11th joules. That's a huge amount of energy. Where is the energy coming from? Well, there's a thing called the nuclear binding energy, and that is the energy required to break a nucleus into its nucleons, or it can be expressed as the energy released when the nucleus is formed. The mass of a nuclide is always smaller. So do you remember when we were calculating average atomic masses, that if we talked about, let's say, looking at our periodic table, I'm talking about, let's do something small, carbon 14. The isotope carbon 14, the mass number is 14, which means it has 8 neutrons and 6 protons. And carbon with atomic number 6 puts it down there at the bottom of our band of stability, which means that it's below 20, atomic number below 20. So carbon is most stable when it has an equal number, 6 and 6, 12 being the mass number. So carbon 14 is unstable because it has too many neutrons. Anyway, if I gave you the mass of carbon 14 when we were calculating average atomic masses, the real mass of that isotope, it wouldn't be 14, it'd be 13.9, whatever. And the difference in that mass is that difference in mass is converted to energy so that you can keep that nucleus together. The binding energy is the energy associated with the strong force that holds it together. The mass differences between the two, between carbon-14 and its real mass, is this nuclear binding energy, and that's the energy that's given off when you do nuclear reactions. So, a lot of energy coming from Einstein's famous equation. We can calculate it. The nucleon binding energy. I've got a graph here. Let's make it a little bit larger. So what it's showing here, and it's kind of fuzzy because the resolution is not very good, is that I can calculate the nucleon binding energy for different isotopes. And that's what it's showing here, very fuzzy, I know. But if I am small, then those nuclei can be fused. If I'm larger, then the only way that fission is the way to access the nucleon binding energy. So how do you tap that energy? Well, fission is a way, and that's the first type of nuclear power that we have explored starting in World War II. And what happens in fission is you bombard a large unstable nucleus like uranium or plutonium, and you, with enough nucleus, if you get the neutron is traveling at a sufficient speed, you can break that unstable nucleus into two daughter nuclides. In this case, it'd be a krypton and a barium. But in the process of splitting it, you get additional neutrons. Those additional neutrons then are able to hit other atoms of uranium or plutonium, and you end up with a chain reaction. One thing that you need to actually make this happen, it's kind of like an activation energy, is a critical mass. So enough slow-moving neutrons are needed to sustain the chain reaction. Bombardment of the radioactive nuclide with a neutron starts the process, but you have to have enough of the radioactive substance in order to sustain a chain reaction. So this is a depiction of a chain reaction. So you hit one nucleus with a that's moving rather fast. It produces additional slower moving neutrons that hit more nuclei, and it kind of builds from there. So it's great, get a lot of energy out of it. However, there are some undesirable aspects. First and foremost is the materials that are produced. The smaller nuclei produced are themselves radioactive, and in the case of a common byproduct of nuclear fission, strontium-90, the half-life is 28.8 years. At this rate of decay, you would have to store the byproducts of nuclear fission, what's left over after you've produced the nuclear power, for 600 years. How do you transport and or design a containment unit that is leak-proof for 600 years? In the United States, we do not transport nuclear waste or reprocess them as is done in other countries. Other countries are not as squeamish about nuclear power as we are. However, I am actually kind of glad that we're a little squeamish about it, because I don't think that we have solved the problem sufficiently. But given our appetite for energy, we're going to have to probably come back to looking at nuclear power. And we can certainly learn from other countries that have been using it for a lot longer and on a larger scale than we have. Fusion is viewed as the savior, and most of you are probably too young to remember the brouhaha over cold fusion that happened several years back, probably before you were born. Some scientists said they had figured out that they could do fusion at much lower temperatures than this. This is what the sun and the stars do, how they do fusion. You've got such a high temperature there that you can take light nuclei and you can fuse them together to make heavier nuclei. So this is a typical fusion equation. But what's needed there is several million kelvins, and it turned out that it was a hoax, and cold fusion is not possible, not yet. But it is a clean source. You don't have radioactive byproducts. But how do we do it when we're not a star? Well, that pretty much wraps up just the background about nuclear chemistry that we're going to talk about. We're going to do a few problems here, so at least you've dipped your hand in it, and that will conclude. So I have taken these problems into the program where I can write. And so we'll start off with number 1. So radioactivity originates where in an atom? If you said the nucleus, you would be correct. So the nucleus. All right. Identify the parent and daughter nuclides. Let me get some full screen action going on here. There we go. Hold on just one sec. I'll make this just a little bit larger. And what kind of radioactivity is involved. So in this equation here, this is the parent, and this is the daughter, and the type of radioactive decay is alpha. Now we're going to write some equations for the alpha decay of each nuclide. So I'll do that starting over here for 3. All right. 3A, we're starting with 218 polonium. So one of the nice things about doing nuclear chemistry is that you at least get to explore some elements we haven't talked about, because we don't really talk about the chemistry of these larger radioactive elements, because that's pretty much what they do, and they're not very, they're radioactive and they're not very useful in terms of regular chemistry. However, we do use that radioactivity to our advantage in doing carbon dating and for chemotherapy and so on. All right, so alpha particle has to be one of your products. And now what you do is you have your periodic table in front of you, and you see polonium has a mass number of 84, so you have to look that up. I didn't write that very well. I'll do better on the next one. So 2 plus what gives me 84? 82. So that gives me a new element, and that new element is lead. And the mass number for this nuclide of Ed, this daughter nuclide, is going to be 218 minus 4, or 214. So again, these mass numbers, 214 and 4, add up to 218, 82 and 2 add up to 84, and that's how you figure these out, is by looking at those mass numbers and atomic numbers. All right, B, this time we're going to start with polonium 214. So 84 again. Alpha particle as a product. Remember, the word decay implies product. Now we're going to have 210. We're once again going to have lead. Remember, I told you lead is a common byproduct. And lead 210 is our daughter nuclide. One more time with polonium. Different isotopes or different nuclides of radionuclides of polonium. Alpha particle, and this time it is lead 206, and that is probably the end of our radioactive series, if indeed this represents a series. D, we're going to do a different one. We're going to do thorium 227, and you have to look up thorium's atomic number, and it is 90, and we're going to do alpha emission one more time. And this time we'll end up with element 80, plus element 88, which is radon, and the mass number is 223. All right. Number 4, we're going to do, I'll just start it down here, then I'll have to just do some, I'll extend the page. 4A, we're going to do beta emission. So we're going to start with lead 211. We're going to end up with a beta particle, and lead has an atomic number of 82. So what plus -1 gives you an 82? It would be 83. Students often want to go down and make it 81. But it's 83 and -1 give you an 82. And then the mass number is not changing, but my element did. And my new element is bismuth. All right. B, you can always stop and try these on your own and then come back and check yourself. Thallium is the element. 207 is the atomic number. I'm sorry, mass number. The atomic number of thallium is 81. Beta emission. So this time it's going to be 82, because 82 and a -1 give you an 81. And it's lead again, and it is lead 207. These heavier isotopes have many, many different isotopes, more so than their lighter elements. Our last one is going to be, C, thorium 234. And that has a mass number of 90, beta emission. So 91 is the mass number of the new element, and that is, I believe it's palladium, but I'm not sure. Let me look. Pa is, it's not palladium. Palladium is Pd. So this is, it's not praseodymium. I'm not sure. I'd have to look up the name. All right, anyway, 91, Pa, and the mass number hasn't changed. It's still 234. All right, and then we're going to do a little page extension. And then D, Pa, 234. And the mass number is 91. Beta emission. And now I'm back to lead again. No, I'm not. Uranium. Sorry, I couldn't get that in. Uranium 234. All right, that is number 4. Number 5, we're going to do positron emission. So cobalt, remember we got lighter nuclei here, and they either undergo beta or positron emission. 55, cobalt. Cobalt has a mass number of 27. The positron has the, it's cobalt, has the symbol of 0, an E, 0 and a 1. So now I want a 26, because 26 and 1 is 27. Mass number doesn't change, and that is the element is iron. B, sodium, 22, and the mass number there is 11. Positron emission. So my new element is element 10, which is neon, and that's neon 22 is the daughter. And C, fluorine 18, and 9 is the atomic number. Positron and 8, which is oxygen. Yeah, oxygen 18. All right, so that is a little practice on doing nuclear equations, different types of radioactivity. Now we're going to go on to still practicing, essentially. Hopefully, let me make it larger. It's bothering me. So, a little bit larger. Now we'll go back to full screen. Okay, so all we're doing here is we're filling in the particle that's missing, identifying the type of radioactivity. So 88 to 89, I need in order to make this side 88, I need a -1. And this is a mistake. It should have been 225. Yes, take the 3 out. So 225. So the mass number is not changing. So my particle is a beta particle. So this is beta emission. All right, in B, we have the particle. It's alpha emission or alpha decay. And my daughter nucleus is going to be element 87, because 87 and 2 make 89. And my mass number is going to be 221. and element 87 is francium. Right? C, alpha emission again. And now I'm back to 87 on the left for my parent nucleus of francium. And the mass number is going to be 221. All right, and then our D is also alpha, and I need 283, element 83, which is bismuth. This 83 and 2 make 85, and 213 is my mass number. All right. In number 7, we are going to start with, I'm going to do it up here, we are going to start with radon 220. And radon has a mass number of, atomic number of 86. And we're going to do 4 reactions, alpha, alpha, beta, alpha. A series, we're doing a small part of the radioactive series, that's why it's called partial, for radon 220. So our first one is alpha, and the other product is 84, which is polonium, and 216 is our mass number. So now the way this works is you take the daughter nucleus and you do the next one. So 216, 84, polonium, another alpha, and the product here is lead, 212. Then I'm going to do a beta with the lead. So the daughter becomes a parent. So we're doing part of that radioactive series type graph that we showed you in the notes. And now we're going to go back to bismuth as our element, and 212 is our mass number. And then one more time, 212 bismuth becomes the parent nucleus, another alpha, and the product at the end of these 4 reactions is thallium, element 81, and the mass number is 217. 217. Oh, I did not do that right. 212. Sorry. 212 is the mass number. I wrote it wrong. 212. And from 212 is 208. Yeah, 208. 81 and 2 is 83. Thallium. Okay? Just double check that. Yes. All right. That's number 7. Number 8. All right. So we're going to do some half-life equations now. We have iodine 131, often used to take images of the thyroid. And this is your initial amount. And how many are left after 1 month? The half-life is 8 days. Now, what's usually done in these simpler half-life equations is that they give you it, they make it easy. They say, now instead of a month, which could be 30 days, 28 days, or 32 days, well, not 32, 31 days, none of which are divisible by 8, you give an even number of half-lives. So you can figure it out pretty easily, because after 1 half-life, I would have 1/2 of this initial amount. After 2 half-lives, I would have half times a half is a quarter. I'd have a quarter of this amount, and so on. So generally, that's the way these questions are asked, but these are a little higher level questions. So we are going to use those equations that I had in the notes. So we're going to need to get in order to use this equation here, the natural log of the amount at time t, this is just a slightly different form of what I have in the notes. This is the one we need to use. I'm going to, and 0 is initial, so that's where our 4 times 10 to the 10 is going to go. But this I don't know. But I'm going to get it from this, k equals 0.693 divided by the half-life. Because half-life is just a application of this equation. It's when I have half of the amount after time t. So k is equal to 0.693 divided by 8. All right? And so your time can be in days. If your half-life is in days, it can be in hours or minutes or seconds or whatever. So that k is 0.0608. Okay, I'm sorry, not for that one. Let's see, where is it? Number 8. 4.0433. That's for a different one. 0.0433 is our half-life for this one. Okay, and now I'm going to plug it in. I want to know how much is left after time t, so that's what I'm solving for. So minus 0.0433 times a month. I'm going to go with, what did I use? 30 days. You could change it. Plus the natural log of this. The 4 times 10 to the 10th. Okay? So 4 e to the 10. So collecting some terms, natural log at time t equals, multiplying those two things out, I get negative 1.299 plus, when I take the natural log of 4 times 10 to the 10th, I get 24.4. Okay. When I collect those two terms, I get 23.11. Now, in order to simplify this, what I have to do, and I do the same thing if it were a log, I have to take the anti-log of both sides. So I'm going to press the shift button where my natural log is on the calculator, and this is what I'm doing. I am saying e to the ln of nt equals e to the 23.11. This becomes just this, and that, when you plug it into the calculator, is 1.09 times 10 to the 10th. Let me do that one more time. I think I have my exponent wrong. So find your natural log on the calculator. I'm going to put in 23.11 and take the anti-log. Yep, that's it. 1.09 times 10 to the 10th. Okay, we start off, yeah, all right. So that is the amount after 30 days. When different calculators are different. On the one I'm just using just now, I could put in the number 23.11 and then and then put in shift natural log. Some calculators you have to do shift natural log or shift log and then put the number in. You'll figure it out on your calculator. All right. That is the first application of the first order kinetics equation for decay. We're going to do some more. So number 8. Oh man. Okay, yeah, I was right before. Okay, thought I was looking at the wrong one. All right, I said number 8 earlier when it was number. Do I have 2 number 8s? 131. I do have 2 number 8s. Craziness. Okay. Well, then that's 9, 10, 11, and 12. So we've got another decay. We've got a half-life of 11.4 days. And then we want to know how long will it take for a 2.240 mole sample to decay to this many moles. Well, I did the math, and this, again, is not an even number. It's not like 3 half-lives or 4 half-lives. So we're going to have to use that same equation. We're going to take K, we've got to get our rate constant, divided by the half-life, 11.4 days. Okay, so when we put our time in, when we solve for time in our other equation, it'll be in days. So K is equal to 0.0608 and then I'm going to plug that into ln at time t, the amount at time t, is equal to negative 0.0608 t, because I want to know the time it takes, plus the natural log of the original amount, which was 0.240. Now, this is what we got. I have my time, the amount at time t, should have put that in there. It is 5 times 10 to the minus 2 moles. So I'm going to take the natural log and then I'm going to solve for t. Now what I could have done is put this up exactly as it appears in the notes, but I didn't do that. Not here anyway. Then I solve for time t. So when I take the natural log of 5 times 10 to the minus 2, and so this is what I'm saying. If I do natural log of 5 times 10 to the minus 2 divided by 0.240, if I take ln of this minus this, because I'm bringing it to the other side, it's the same as doing this. And that's the form of the equation that's in the notes. Nt over N0 equals minus Kt. All right. So when I do this, I get negative 1.57 on this side equals negative 0.0608 for that K times T becomes positive, good, and I end up with 25.8 days, which is not a even multiple of 11.4, but that's okay. We have an equation that's easy to use, and we can figure it out even when it's not even. All right, number 9. One of the nuclides in spent nuclear fuel, uranium-235, an alpha emitter, has a half-life of 703 million years. Now this one's pretty easy because it asks how long will it take to 1/8. Well, 1/8 is 3 half-lives. Okay, so I take 3 times equals 3 half-lives. That's an eighth. So all I have to do is multiply 703 million times 3, and that number is going to be so large, I'm going to put it in scientific notation, and that is 2.12 times 10 to the 9th years. So that's a lot of years to have spent nuclear fuel that's radioactive around. Number 10. 68 milligram sample is administered to a patient to obtain an image of her thyroid. Half-life is 12 hours. How much remains after 4 days? Okay. Well, 4 days is 96 hours. 4 times 24 equals 46 hours. 96 hours. Got to compare, if the half-life's in hours, I need to know the length of time in the same amount, in the same unit. That's 8 half-lives. So this is kind of how we do it without using the equation. You look at the amount of time, you divide by the half-life, and you see that it's 8. It's a multiple. It is an even multiple here. It's 8 half-lives. So essentially what you'll be doing is you'll be taking 1/2, like we did up here. 1/8 is 1/2 to the 3, so that's why it's, okay. 1/2 to the 8th power is how much that is equal to 3.91 times 10 to the minus 3. And then I will multiply that times, so it's like taking like we did up here, we took the fact that it was 1/8, we did 3 half-lives, multiplied times half-life times 3. Here we know it's 8 half-lives, so my multiplier is here, 1/2 to the 8th, 3.91 times 10 to the minus 3 times the 68 milligrams. So after 8 half-lives, which is 96 hours, I will be left with 0.266 milligrams. All right, you could use this equation here, the one right here, okay, and you get the same answer. All right, last one, number 11, about carbon dating. So a layer of peat buried under glacial sediments has 25% of the carbon-14 found in living organisms. How long ago was this ice age? Well, 25% is 1/4, which is 2 half-lives. You'd have 1/4 of what you originally had. So I am going to take, so that's 2 half-lives, and the half-life of carbon-14 is 5,715 years times 2. It's 2 half-lives. So that peat has been buried for 11,430 years. And that's our last problem for radioactivity and nuclear chemistry. And it's just a small dose, pun. And that concludes lecture 24.